you for joining the webinar. Oh, let me try it again. Recordings in progress. Good evening, and thank you for joining the webinar this evening. The webinar is going to get started as we just open it up digitally. Let's let other attendees join the event. While we're waiting, please answer a question. This question and answer format will be used during the webinar to improve knowledge transfer in both directions. All right, we're about 2 minutes after you've had a chance to answer the question. So hello and welcome to the Quest for Gold, Exploring Nuclear Transmutation, presented by the American Nuclear Society. This evening's webinar is part of the ANS Educator Training program, which is specifically developed for elementary through high school teachers. The question that we pose, can you make gold? I see 76% of you got it right. So what Candace is going to do is reinforce what you already know for those that answered it correctly. And for the other ones, you're going to learn how, through manipulation of the nucleus, we can make gold. So my name is Eric Lowen. I had the opportunity to be the president of the society in 2011 and 2012. I currently work at GE Hitachi Nuclear Energy, or GE Vernova, and I'm the chief engineer there. So I'm tonight's host, and we'll turn it over to our speaker with just a few remarks. Any questions that you have, please use the Q&A feature. As many questions as possible will be addressed. The event is recorded, and a link to that recording will be emailed to each of the registrants. Certificates of attendance for today's webinar are available upon request. Just email us at askanything@ans.org to request a certificate. If you'd like to learn more about other ANS educational events, programs, resources, you can visit the ANS website at ans.org, or email our Senior Manager of STEM Programs, Uchenna, who's going to drop his email address into the link. So for the educators that are in the audience, if you'd like to have an ANS member to visit your classroom, either virtually or in real life, please send your request to askanything@ans.org. And to our ANS members that are listening tonight, ANS Nuclear Ambassador Program offers members free training in K-12 nuclear education outreach. Contact Uchenna if you are interested in getting training for yourself or your organization. And finally, please adhere to the ANS Code of Ethics and Respectful Behavior Policy, which can be found on our website. Today's presenter that I've known for a long time and worked side by side with her at many teachers' workshops on Saturdays is Candace Davison. She has been a STEM educator for more than 30 years, including at Penn State University, where she most recently was the Assistant Director of Education Outreach and Coordination for the Gamma Irradiation Facility at Penn State Radiation Science and Engineering Center. She was the first woman to be licensed as a senior reactor operator at the university's Triga reactor. Candace joined the Penn State in Engineering Technology Projects Group in the Nuclear Engineering Department, where she developed programs and presentations on energy, nuclear technology, radon, and radioactive waste. She began developing teacher training programs as a member of the Penn State Nuclear Concepts and Technology Issues Institute. Originally a Pennsylvania-based program, the Institute expanded to include science educators from the U.S. and abroad. She has conducted educational workshops for Contemporary Physics Education Program, CPEP, and the Penn State Center for Science and for Center of Science in the Schools. So as I mentioned when I introduced her, she and I have done teachers workshops. She's supported webinars, so you are in good hands. Welcome, Candace.
Hello. Thank you, Eric, and thank you for this introduction. And why are we doing this program? Well, one of the reasons is I've always been interested and intrigued by alchemy. And so we decided this would be a great opportunity to talk about the nuclear activities and what we can do with the nucleus. So we'll start by sharing my screen. When I joined the Radiation Science and Engineering Center, I did work at the nuclear reactor, which is the background that you see behind me, and we did make radioactive elements. And that's part of what we'll be discussing today, and learn about the concept of transmutation. And that's what alchemy is. It's transmuting, changing elements from one form into another. And there was a lot of interest and research on that for many, many years. As we discuss alchemy, we need to actually go back to the ancient scholars and some of the theories and concepts that they had years ago. So I'll just go through a little bit of brief information on this, and starting for even before 500 BC, but people were wondering, what is this? What is this earth made of? What makes up all this stuff? And they recognized there are different things. So Anaxagoras said, well, matter there's no smaller part, right? It can be infinitely indivisible, right? It can be, there's no very, very, very small part. So that was his theory. And then there was, and you might have heard of the earth, air, fire, and water, right? There are 4 basic elements. And if we change the proportions of those, we're going to get these different components, right? These different other things from those 4 basic elements. But Empedocles also talked about the conservation of mass. So again, some of this background really reinforced what we know today, right? So this is interesting, conservation of mass. That's still good. Democritus is, if you've studied nuclear atoms and things, he is credited with that first concept of that very small building block of things, the atom, and that there's a lot of empty space between them, and they're always in motion. And that there are more than 4 elements, and talked about the universe, right? These smaller atoms can be formed together to make larger substances. Aristotle and Plato, though, only believed there were back to the 4 elements, and that the elements can transform into one another. This is going back to the alchemy idea. And Alexander the Great, who learned under Aristotle, also felt that alchemy was the only science worth pursuing. So we kind of have a little bit of background of, what is this science, or science, religion, philosophy, all kind of combined. As I was doing some research for this, I came across a Cleopatra Chrysopia, and that term, Chrysopia, is actually the term of transforming something into gold. And she is credited with putting together a scroll, which they found, and the image on the right is of a distillation column, and that's still used today, that type of distillation, and did a lot of research on chemistry and refining materials. So as we've learned more about atoms and these elements, we're building that information. Now again, all this rolls into what we're going to be talking about today, those building blocks and how we can maybe transform those into something else. So the next building block would be the periodic table of the elements. And Mendeleev put together the basics of what we see today, even had spaces for the elements that hadn't been discovered yet in the correct places, and included information about what properties they might have. So we have our periodic table today where we have the chemicals, the basics of chemistry. And as we're continuing along, we're going to go into the nuclear part of this, and that's where I came in. And as I mentioned, I was always intrigued by this whole idea of transforming elements and learning about how we could do that and about these nuclear reactions. And ANS has several webinars that include more detail on some of the things I'm going to talk about today. So you can go more into those details, and we'll discuss those later. So I'm going to just brush a little bit on the background of basics of nuclear notation and nuclear, engineering, nuclear physics. The way we write the basics of an atom, and I know a lot of you have this background, but just reviewing, we have the chemical symbol, which we're relating here as X, the mass number, which is the total protons and neutrons on the above, and then the atomic number, Z, below. And usually you don't need to write the Z number below unless you're doing nuclear equations. So most people, if you look on the bottom, you see that there's carbon 12, right, without the 6, and carbon 13 and carbon 14. So then that leads us to isotopes, which, as we mentioned back here, we have isotopes of carbon. I'm going to talk about the isotopes of hydrogen. I just want to mention that for simplicity's sake, we're showing the electron in a ring. We all know it's an electron cloud, but that's kind of hard to make a beehive looking thing on a graph. So we're using just the simplicity image here of the hydrogen atom. So hydrogen 1 has 1 proton, hydrogen 2 has 1 proton, but it also has a neutron, and it's also called deuterium. And then hydrogen 3, tritium 3, components in the nucleus, still has the 1 proton, and then has the 2 neutrons. So those are our isotopes of hydrogen. An isotope has the same chemical, right? It has the same number. They all have the same number of protons and electrons. The only difference is the number of neutrons, so their mass is slightly different. But chemically, they react the same, right? Because of the electron interaction. And that's where chemistry differs from the nuclear that we're going to get into, because chemistry is more about the electrons, right? Electron interactions. So why are some atoms radioactive? Well, you see on the periodic table here, we've highlighted the radioactive elements, and you might notice some interesting things about where these are located on the periodic table. And we'll go into a little bit more about this as we continue with the webinar. And this has to do with why some elements are more stable than others. So it has to do with the stability of the nucleus, and that has to do with the protons and neutrons in the nucleus. There's an ideal arrangement or proportion of protons and neutrons. If the nucleus doesn't have that ideal proportion, it's considered unstable or maybe energetic, and so it wants to release particles to become more stable, and that is giving off radiation. If it's still unstable after releases a particle, maybe it will continue to release more particles or waves, and that's called radioactive decay. So just a review that radiation is energy that travels by particles or waves. And when those particles are released, we have a different element, right? If we're changing the nucleus, we're changing the element because now we have a different number of protons in the nucleus. So in this case, this is the radioactive decay chain where uranium decays to thorium and then protactinium, then back up to uranium, down to thorium, radium, radon, polonium, and you can see it goes all the way down to lead. And a lot of people are like, oh, that's right, lead, that's a stable, right? But this lead, this isotope of lead, 206, is the stable. These other isotopes are not stable, right? They don't have the right proportion of protons and neutrons. Oh, well, I said alpha. Let's just go quickly over what an alpha, beta, and gamma radiation is. Alpha particle is a helium nucleus that comes, again, it's a big chunk that comes from the nucleus. So if it's a large nucleus, typically an alpha particle is released from a large nucleus. And now we have a smaller nucleus, right? Beta minus is an electron that comes from the nucleus. And that is when a neutron, if you think of a neutron as a proton and electron, the electron leaves, and now that leaves the proton in there. So we lose the neutron, it becomes a proton, and that electron shoots away. And then we have gamma rays, which are just photons or packages of energy, which when the nucleus emits these particles, it needs to kind of shift and reconfigure. That's my concept of a gamma ray. And that means that the photon will just be released, and now the atom is more stable, right? It's just kind of shifted around and reconfigured. So what makes the nucleus unstable? Well, if you look at this line, you see that at the low energy, low Z numbers, right, from 0 to about 20, we have the same number of protons and neutrons in the nucleus, like helium-4, lithium-6, carbon-12, nitrogen-14. Okay, so carbon-12 has 6 protons and 6 neutrons. Nitrogen-14 has 7 protons and 7 neutrons. Oxygen-16, 8 protons and 8 neutrons. So it has the same number of protons and neutrons. But as we go up and increase the number of protons, we see that all of a sudden we have more neutrons than we do protons in the nucleus. Okay, the line of stability differs. It's not a 1-to-1 ratio anymore. And that's to keep the nucleus stable. If you have too many positive charges, the protons, they're going to start to repel. So more neutrons helps to diffuse those positive repelling forces. So if you look at chemistry books, you've seen graphs probably like this. But nuclear people are more interested in neutrons. So if you look at the nuclear books, you'll see a graph that looks like this. It's a little bit different. All it's done is we've actually switched the axes, right? Instead of protons on the x-axis, we have the neutrons on the x-axis. And we have the proton on the y-axis. So that you can see your line of stability, and then you can also see your z equals n, your 45-degree angle. And with the neutron chart, your neutron-based chart, you can see that the line of stability is below that. Okay, we're adding more neutrons. Either way, it just depends on how you make the chart. But going forward in the presentation, we are going to use the nuclear format with the neutron number along the x-axis and the proton number on the y-axis. So to review, only certain combinations of neutrons and protons make the atom stable, and that's when the attractive and repulsive forces are in balance. If they're not in balance, again, they're going to release a particle or wave to become more stable. So atoms that aren't along that line of stability are going to release particles to get closer and closer to the line of stability. And that means they might have more than one decay to get to that point. A way to kind of look at this, and I'm going to go into how we teach this. Whenever I was working at Penn State, people would run up to the chart of the nuclides. They would look at the chart and say, oh, it gives an alpha particle off and becomes that. And I was so confused. How do they know this? Well, this is, first of all, there's a little graph that helps you, and this is the graph. If this is your original nucleus and it releases an alpha particle, it's going to drop down 2 protons, because an alpha is 2 protons and 2 neutrons. So we're going to reduce by 2 protons and 2 neutrons, and your new nucleus is going to be located here. If it's a beta minus emitter, it's now, remember, the neutron becomes a proton. So we reduce the number of neutrons. So we reduce the number of neutrons, goes to the left one. We increase the number of protons, and now this is your beta minus, decay product. Well, that helped, but as I was teaching this to a group of students, we came across a fun thing to do to help reinforce these concepts, this concept of transmutation, and what does this become once it releases these particles? And this is called the radioactivity game. And the way this works is you start at any square that has there's a slight circle that's grayed out. So you can start at any one of those. And then you need a number cube to help you, so we've got our little fancy number cube, right? 1 through 6. And then all you need to do is roll that number cube. And if you roll the correct number for the type of decay that you need, then you keep rolling, right? You keep going on your turn. This game was actually proposed, it was written in the physics teacher many, many years ago, and then the New York State educational series also had it. We put it on 11 by 17 paper and then just laminate it and then use some puzzle, pieces, any type of, coins, whatever to, for each student to use to keep their place. And then we have the number cubes and then they play the game. So we're gonna go through this. The first place that I'm going to start is uranium-238. We're going to go through, this is that radioactive decay series. As I mentioned, there are 4 radioactive decay series, only 3 in nature now. And we're going to start with uranium-238. Now the first question, and we're going to put up a poll just to make sure everybody knows how to play the game. And as I said, this really facilitates understanding, especially it's kinesthetic, it's kind of fun, the students really enjoyed it, of how this decay process works. So what number on the number cube, and Uchenna is going to put this, I think, up in the poll up, there we are, do you need to roll, right, to move? So what number on the number cube, remember there's 1 through 6, do you need to roll to move? And we'll give you a few minutes to answer. And there could be more than one answer, but just one answer is fine. And do we have the results yet of the survey? There we go. All right. So we've got a whole bunch. That's good, which is why I wanted to do this, to make sure people understood how to play this game. So we've got 39% and 29%. So 5 or 6. That is 5 or 6 is the correct answer because we need to alpha decay. So I'll go through that, and this is good because this helps ensure that the concept and the understanding is there. So you see that uranium-238, it goes in this direction, right? This is alpha decay. We're going down 2 over 2, right? We're reducing 2 protons, 2 neutrons. So this is our alpha decay. So in order to alpha decay, you had to roll a 5 or 6. Okay, so let's... Now we're at a spot where what type of decay do we need to roll to move? Again, it's either the long arrow down or the short arrow up. Think about your decay, right? What do we need to roll to move for this part of my turn? So as long as I roll the correct number on the number cube, then I can continue my turn. My turn lasts as long as I'm rolling the correct type of decay. And again, 5 or 6 is alpha, 2, 3, 4 is beta, and 1 is gamma. So we'll put the survey, we're going to do another survey, put the survey back up, and see if you can determine the correct number, 2, 3, 4, 5, 6, or 1 for the decay.
Candace, I just want to double check. Do we want to put the uranium one again, or is this the thorium?
That's the thorium. We're at
Okay.
thorium. Yep. We're at
Just wanted to
thorium
make
234. Yeah, we went from uranium 238 down to thorium 234.
All right, there you go.
So we're starting at thorium 234. Where does this go from here? Does it alpha decay or does it beta decay? And if it's alpha, it's 5 or 6. If it's beta, it's 2, 3, or 4. And if it's gamma, it's 1. Okay. All right. And so better explaining, and that's good because I was told by my daughter I didn't explain things very well. So hopefully we're getting this. A 2, 3, 4 is the correct answer. It was beta minus decay. And so you can see most everybody did the correct answer. All right. So if I rolled a 3, I would roll again, and that would be a beta decay from thorium to protactinium, and then I'd have to beta decay again, so I'd have to roll a 2, 3, or 4 to keep moving. Now I'm back up to uranium, and I don't know if you remember, but back before there was the uranium decay series, and it went back to uranium again. Now we're going to go back down to thorium with an alpha decay, so that would be the next roll. And then we have several alpha decays. So again, typically the very large nuclei, to get more stable, will give off big chunks, right? It's easier to give off a big chunk and you're getting more stable more quickly, right? But that is such a large chunk to come out of the nucleus that the half-lives aren't always really short. They can be long, but we're alpha decaying from thorium down to radium. And this is another alpha decay down to radon, which again, and this is transmuting, right? This is transmutation. So we went from radium, and all those elements up until there to radium are all solids. They're solid materials. But radon, which comes from the decay of radium, is a gas. And I don't know if you've heard of radon gas, but it can come up into your home, right? And concentrate in buildings. And we also have a webinar on that. Okay, radon has a 3-point-something day half-life, and then it goes from this gas to polonium, which is a solid. And that just blows my mind to think of this gas all of a sudden becoming a solid element, right? It's an atom, but it's solid. So we are down to polonium, and at this point in the game, and again, if I was rolling the correct numbers, and if I had rolled back here, if I had rolled a 2, 3, or 4, I would just, give my number cube over to somebody else. I'm done with my turn. If I roll a 1, we changed the rules to say that you just keep rolling again. Gamma emission, you don't move, but you also don't lose your turn. It just helps the game go a little faster and, gives us a little bit quicker results. So this time we're going to roll a 5 or 6 to go down to polonium. At this point, though, I could roll anything. 1, 2, 3, 4, 5, or 6, I would still get to roll again. So if I roll a 2, 3, or 4, which is beta minus, I'm going to go up to that position. And then now at this point, I have to roll a 5 or 6. And you might see, where's my thing, that here I do beta minus decay and then alpha decay. And at this point, it's alpha decay and then beta minus decay. They end up at the same point. So it's kind of a juncture and then ending up at the same point. And there is a predominant path for this decay series, but there's also evidence of these other pathways happening, right? And from here, you continue on, till you get to one of these triangles. And in the case of uranium-238, it ends up at lead-206. And you can see that there's 3 leads and a bismuth, those that are the stable parts of this. One of the things we found with this is it helps with the conceptualization of when alpha is emitted, we are actually changing the nucleus. We're changing the elements. Same with beta particles, coming from the nucleus. And the gamma does not change those elements. And for your more advanced students, you can actually, as you go through each turn, write out the equation. So the first one was uranium-238. It released, an alpha particle and became thorium-234. And you can see the top number, 238, 234 plus 4 is 238. The bottom number, 92, and the bottom number is 90 plus 2, 92. So the top and bottom need to add up on both sides of the equation. Remember the conservation of mass? Yes, that's still there. Beta minus decay, thorium decayed by beta emission to protactinium. And in this case, again, the top number is the same. And the bottom number, we have 90 for thorium. Remember, the neutron became a proton, so we increased the number of protons, and we write beta minus as a -1 down here. And we also have the antineutrino. And then your gamma decay is just an excited state. And so in the case of technetium-99m, which is used for medical diagnostics, it becomes technetium-99 with about a 6-hour half-life for a metastable state. It's pretty long. But that gamma emission is what they use in the diagnoses. Right, so these are the decay equations, and that's helping again to, writing it out, seeing how this decay process works, that transmutation from one element to another. And we're going to move on to one of my favorite things, the chart of the nuclides. And this has a lot of information. We're going to put the link in the chat, so if you would like, you can follow along. And I'm going to close, stop sharing, and I'm going to go into sharing my screen again. So I'm bringing up the chart of the nuclides, the live chart. Here we are. And this has a lot of information. One of the things is you can notice it just looks like the line of stability that we've shown you. It's the neutron number on the bottom, proton number on the y-axis, and we can look at a lot of different things. But first of all, we're looking at the line of stability, and those are the black boxes. You might notice that this bluish color, that's the beta minus decay. So everything below the line of stability, in order to get up to the line of stability, at least on this bottom part, is beta minus decay. We have alpha decay predominantly at the top of the chart. Again, the large nuclei are going to give up bigger particles to become more stable. We also have above the line of stability, we have electron capture or beta plus emission, because they're trying to get down, and diagonally downward toward the line of stability. So down this way. So you can see, you can bring up almost anything here, but it talks about, what type of decay, let's see, the decay type here, it says electron capture beta plus 100%, and it also gives the half-life. And another comment is, as you explore this, is you might notice that as you get further and further from the line of stability, the half-lives tend to get shorter and shorter, because those nuclei are very unstable, because again, they have a very big difference of proton-neutron ratio. They're not to that ideal proton-neutron ratio. But one thing we can do is explore, just type in C for carbon, and let's look at how many isotopes of carbon we have. Well, this brings up all the carbon isotopes, and we see that there are 2 isotopes that are stable, carbon-12 and carbon-13. We can also look at carbon-14 and find out, oh, look, it has a 5,700-year half-life. So there's lots of information, way more than you really need, but if you want all this information, you can get it. We can also go to specific nuclides. So if I wanted to type in maybe 197 gold, I could bring that up, and it gives me gold 197, which is stable. It also gives me the elements that have the same mass number in that diagonal chain there. So a lot of things you can do with the chart of the nuclides, lots of things to explore. And by doing this, it tells, you can also look at like the decay radiation, and it'll tell you what it decays into, right? If you don't know how to do the movements that we had before. Whoops. So I'm going to go back to, then I'm going to share the screen again, and all right. Back to the chart of the nuclides. All right, so those were the decay processes. You can learn about the isotopes, which ones are stable, their abundance, because if you have more than one stable isotope, you're going to have their natural abundance. It'll tell you like this one's 50%, maybe 49% and 51%, 100% if there's only one stable isotope. So you can learn a lot about that. We're moving now from the basic reactions to now producing radioactive materials, which they've been doing for many years. And as I mentioned at the reactor, we added a neutron from the nuclear reactor, and we got something radioactive. So in this case, we have our target nucleus, and then we add a neutron, and we get something that's giving off a gamma ray, because again, it's added that neutron is going to shift and release a gamma ray. And we can make possibly a radioactive element. In the case of cobalt, we take cobalt 59, add a neutron, and get radioactive cobalt 60. And as Eric mentioned, I was involved in the cobalt irradiation facility at Penn State. So we did a lot of things with radioactive cobalt. It has high energy gamma rays that don't make things radioactive, but they can be used for lots of different applications. We can also, if we go from the target nucleus down diagonally to, this is the neutron-proton reaction, and let's look at what we might have from that. Well, one of the neutron-proton reactions that you may be familiar with is carbon-14. Okay, the production of carbon-14 is a neutron-proton reaction with cosmic radiation that forms neutrons in the atmosphere. That interacts with the nitrogen in the air. Our air is about 70% nitrogen, right? And so that neutron comes into that nitrogen-14 atom, and that gives off a proton and leaves us with carbon-14. Now, the interesting thing is when you go back to this, notice where that, target nucleus starts here. This is your resulting, nucleus, right? It's down here. Remember the line of stability and beta decay was a direction going up in this direction, right? Going up diagonally that way. Well, when carbon-14 decays, it becomes nitrogen-14 by emitting a beta minus. So an NP reaction, it's kind of a circular thing, right? Neutron, proton goes below the line of stability and then it wants to come back up toward the line of stability by releasing a beta minus particle. Another thought, and this we're going to put the direct link to this in the chat, is how to make fluorine-18. So we're going to go into, again, how do we produce these radioactive isotopes? Fluorine-18 is used in PET scans. It's used quite a bit. Well, how could we make fluorine-18? Well, let's go back to that little diagram with the target nucleus. Now remember, we're trying to make this, the one in red, fluorine-18. So that's what we're trying to get to. That's not our target. We want to start with a stable target. Well, why don't we start with fluorine-19, right? And then just, we would move this direction, right? From fluorine-19 to fluorine-18. And it would be, say, a photon-neutron reaction. That sounds easy. The only issue with that is when you have fluorine-19 and fluorine-18, you have a stable fluorine and a radioactive one. It's very difficult to separate those because it's only by that one atomic mass unit. So very, very little, mass difference. It can be done, but it's pretty difficult to do. So it's usually in making radioactive elements is you make it with a different chemical, so then you can chemically separate the two. So in this case, we would either use oxygen or neon. Neon is a stable, it's a noble gas. So it's really hard to have, to really, affect that nucleus because it's a noble gas is really, really stable. That leaves oxygen. So let's look at the possibilities of making fluorine-18 with oxygen. Well, one option is using oxygen-18, which is down here. And remember, this would be our target, and we're going up, diagonally up, right? So target nucleus, diagonally up. What do we need to make fluorine-18 if we start with oxygen-18? Well, we're going to need that proton-neutron reaction. Okay, let's start now with, instead of oxygen-18, which is not very abundant, maybe oxygen-16. That's very abundant, right? The abundance is pretty high. Let's start with that as our target. And again, we're going to go up in that direction, so diagonally that way. So target going in this direction. These would be the types of reactions that we'd want to make fluorine-18 from oxygen-16. So let's look at those, and that would be helium-3 proton, an alpha, and a neutron proton. And then there's also a tritium and neutron reaction. It could be. So this is how we can produce different isotopes using either an accelerator, say an accelerated proton, or an accelerated, helium-3. So these are charged particles that are accelerated, and they can then get into the nucleus and then make a change. The neutrons, if you're using a neutron to make changes, which we do with the nuclear reactor, it also depends on the neutron energy. Certain reactions happen better with lower neutron energies, and other reactions need the really high neutron energies, especially if you're getting particles that are coming out, like an NP or something like that. The neutron energy has to be higher typically. So now, for the moment we've all been waiting for, and let me go. I am going to put on my alchemy hat, because we are going to make gold. So let's see what reactions we need. This is what we've been talking about today. How do we make gold? So let me take off. I've got my hat on. There we go. And I'm going to put the chart up, and also you're going to get this link this is the chart that I have, but if you use the link, you can also go to the live chart of the Nuclides and figure out what you might need to make gold. Uchenna is going to put the survey in with some answers. And again, there are more than one possible answer. We've given several possibilities, but to look at your stable elements to start with, your stable isotopes, and also look at the little graph here to see if you can figure out, starting with what target nucleus can get us to gold 197. Right now we're trying to make gold 197. And we'll see how are we doing. Got a quick survey up, and I was going to suggest that we play the neutron dance from what that was, the Pointer Sisters sang, but there's the whole playing videos and playing music. So, but check it out. That's a good song.
Responses are still rolling in, Candace. I'd say give
Okay.
them 20, 30
Yeah, it
seconds.
takes a little bit of time because they're kind of looking at trying to figure out what your target is. And to me, it's kind of going backwards because I'm so used to, here's the target, there's where I'm going, versus, oh, here's where I need to go, how do I get there, right? Okay. Well, let's go to the survey answers. We've got platinum 196, and let's see. I don't see I lost the order. Platinum 196, a proton gamma reaction. Mercury 198, a gamma proton reaction, and mercury 199, a neutron tritium reaction. So let's look at those. These are of the ones that were listed, the possible. So platinum 196. So this is platinum 196 down here. Let me get the laser pointer. Platinum 196, and we want to go up. So target nucleus up. So a proton gamma reaction would be any of these three would, and again, it depends on what you have and accelerators and energies and things. Mercury 198, which is right above that. So we're going down. So it would be this direction. So any of these, so gamma proton reaction would be, and again, it would be a very, very high energy photon to do that. And then Mercury 199, which is going this direction diagonally. So we're going that direction. So a neutron tritium or any of these would potentially help you to make that gold. Now, one of the things that we were talking about before this is that, platinum is a pretty rare metal. And before, years ago, it was actually more expensive than gold. So changing platinum into gold is probably not, what you want to do. Mercury, I don't know if I want to play with mercury very much. So, that's a metal that's a little bit potentially hazardous, right? So do we want to play with mercury and make that into gold? But we can also make radioactive gold too from some of these reactions. And these aren't the only reactions, but it's just a way to, say, yes, we can make gold. Certainly with protons, hitting platinum with protons and things, we can make gold. And there are a few interesting articles that I read about Glenn Seaborg, who was, the Lawrence Berkeley Accelerator, and talking about making gold, from that. Now, again, very small amounts of gold, but still truly making an alchemy reaction. Well, the last thing I wanted to talk about before we get to questions is this Isotope Discovery App that is a great resource, and also it kind of meshes with what we were talking about today. So this will be in your link, and I'm going to go to it. So stop share. All right. I'll bring this up and just do a quick overview of the Isotope Discovery App before we have questions. First of all, if you do the user guide, it'll tell you how to manipulate through it. It's really easy though. For example, if we wanted to double click on this and click and hold, I can move it. And let's just go down to gold. And we find that gold 197 is used in jewelry, right? And it's stable. This is a stable form of gold. But let's, make gold 195. So we reduce the number of neutrons, right? Because we still keep the same number of protons. Gold 195 is actually used in rheumatoid arthritis treatment. It's radioactive. It has a reasonable, several, 100-day or so half-life. So it can be injected for rheumatoid arthritis. And so you can explore just by, moving this the bar down here to change the different atoms. You get the different atoms and learning about how those protons and neutron ratio. As I move that, you might also see that the line of stability on the chart of the nuclides is also, it follows along, as does the table, a periodic table. So you see the chemical, you see the chart of the nuclides, where it is on that, little bit of information about the isotopes, and there's lots of information about that. And then, the nucleus itself, right? The proton-neutron ratio. So students can play with, changing it and finding out, is this really an atom or not, right? Based on the proton and neutron ratio. Well, that I would highly recommend. Again, it's fun to do. It's a great way to explore things. And I'll take off my alchemy hat and go back to the presentation. Right at the very end, just a lot of resources. American Nuclear Society, as I mentioned, the educator training webinars, building the nucleus, decoding radioactive decay, the radioisotope one that talks about all the different isotopes and applications. They're all excellent webinars. The app that we talked about, navigating nuclear curriculum, and lots of resources. And then different resources too that I've used and we've used in many of our workshops. There's a lot, and some of the references. And somebody I think had asked about the slides, and I believe that will be included, right, as far as that goes. So I wanted to leave time for questions because we do have to be done by 7. So let's start with that.
All right. Well, thank you, Candace. we have a question on beta minus decay. So I'll read the question, but I think it's confusion between beta minus and beta plus. So if beta minus decay emits an electron turning a neutron into a proton, can a proton release an electron turning a proton into a single electron? Can a proton go through a beta minus decay? Can a proton be divided into 2 electrons? So I think you got to do. My suggestion is talk about a beta minus and beta plus, and maybe show the chart to show the differences.
Yeah.
Then you can tell them about antimatter and positrons.
So remember we talked about, let me see if I can get to, let's go back up to the chart. That'd be easier. Okay, so, okay.
There we go.
So the beta minus, remember, the original nucleus, beta minus out. So the neutron becomes a proton. If you think of a neutron as a proton electron, that's easy. Electron leaves, you leave a proton. Oh, okay. But now, how do we have a proton change into a neutron? Well, you get into quarks with that, and there's the up and down quarks. I wasn't going to go into that, but basically, you have a proton that becomes a neutron and a positive electron leaves. That's the beta plus. That's the positron, and that's the positron emission tomography. That's what's used, this positive electron. That's antimatter, as Eric mentioned, and a lot of, let me see, there. A lot of, the antimatter doesn't last very long. It's basically electron spinning in the other direction. So your normal electron and your positive electron, right, will actually find each other and annihilate into 2. You'll see 2 gamma rays, photons coming off 180 degrees apart. And that's actually how they detect this when they give you these positron emitting your radioactive nuclides that you're taking to be in the PET scan. They detect those 2 gamma rays and 180 degrees apart, and based on when they hit those detectors, they can figure out with lots of math where that annihilation took place. So yes, it's a little confusing. So that's your beta plus. But the electron capture, that's another electron capture, is a similar kind of thought process where remember we talk about the electrons are just in kind of a beehive, right? Around, is buzzing like bees buzzing around the beehive. If that electron gets real close to the nucleus and maybe it just gets sucked up, right, by a proton, all right, so now that proton becomes a neutron because now it pulled that electron in. So again, the result is the same. Your original nucleus here is going to end up here by either positron emission or electron capture. Did that help?
That was great. So let's talk about alpha particles. Next question, why is alpha particle decay so common? Why does so many unstable nuclei undergo radioactive decay by emitting a helium nucleus, while far fewer cases involve emissions of other nucleon combinations such as a proton or a deuterium or a helium-3 nucleus?
Well, that's a good question. It does have to do with, again, alpha isn't as common, say, as the beta minus beta plus. When you looked at the chart of the table of the nuclides, where was it? Here. Where is it? There. The alphas, it is up here. It's not as common, as I said, as the beta minus or the beta plus, but certainly proton emission and neutron emission aren't as common. And off the top of my head, I can't, but I do remember, there's some reasons, it has to do with the stability and releasing those. Some particles are more difficult to release than others, and it just a simple way. We get more into the nuclear, probabilities and things. So I'm not sure I answered that, but we'll go.
Just blame it on quantum theory.
Right.
The alpha particle has a better quantum state or something like that, if I recall correctly.
Yes.
One of the questions, source of the handouts, can purchase from students. No, you can't purchase them. You just get them for free. So I wouldn't worry about that.
Right.
We do have a game. All right, here's a technical one.
Oh.
The U-238 is found in nature, and is it stable or has a very high half-life? Why did it decay by itself on your chart? So back to uranium-238.
Why did it decay?
Why is it found in nature and
Okay.
is stable? So I think you got to clear up it's not necessarily stable, it just has a long half-life.
It has a very long half-life. We're talking billions of years, but why do you want to get it? But if you have a supernova explosion, you're going to have very, very heavy elements that you wouldn't normally get just by fusion, fusing smaller elements together alone. You need a lot more energy to make these very large elements. And because they're very large, they don't have that, ideal ratio of protons and neutrons, right? So uranium-238 isn't that, have the ideal ratio. So it is radioactive. And so it will, the uranium-238 will eventually all become lead, but it has such a long half-life that it will be a very long time before it all disappears. But there were, like I said, 4 series, and one of the series has completely decayed, which we don't find in nature now because those elements were very short-lived. So.
Right.
Yeah.
One of your fans talked about having a nice hat. We'll not disclose that person. And then we had a question with kind of a statement was just because it can be done doesn't make economic sense of turning platinum to gold. But what we're trying to do as a society is what Candace is trying to do is, if you change nucleus protons, you change the elements.
Right.
So we're not purporting to take platinum and irradiate it. What we're trying to do is to teach that physics and, that old, a lot of people get interested in chemistry because they thought they can make gold. So we appreciate that.
Right. And really the real life applications are making those isotopes that are used to research, cure cancer, right? Do a lot of other things, not, so they are produced either with a reactor or accelerator. And that's kind of what I was talking about. And the other webinar does go into some of those applications, many applications. So yes, I wasn't saying we want to make gold. I think it was a catchy thing and it's always intrigued me, and it doesn't make sense, right? But it is an interesting and fun thing. And so, but you can use that process to figure out how to make other elements, right? How can we make these radioactive isotopes that are used for research and also cancer therapies and things? We're targeting, radioactive elements to go right to the cancer. So that would be great, right? We could just target the cancerous cells with radioactive elements and then being able to get rid of the cancer and things.
So I think we have to admit that we're going for the wow factor. We could say, could we make lead?
Right.
It doesn't sound.
Yeah, that's not.
All right, then it's not as fun. I think this will be our last question. The transmutation process that is known until now is dependent on particle release or absorb, and usually have a tendency, like uranium stairs of decay, and it's kind of feel like we have a barrier regarding material properties, energy, etc. How do you think we can really break this barrier and achieve the perfection of transmutation?
Ooh, boy, if I knew the answer to that, I'd have but there are several programs that used isotopes and looked at like maybe transforming radioactive waste into other things. But, so yes, they are still working on that and yeah, keep researching. Yep.
All right, how about this one? We'll put you on record. Could nuclear transmutation be a viable industrial process for producing, you pick what it is. In this case, they said gold.
Okay.
But
well, yes, not necessarily for gold, but as we mentioned, producing those isotopes that are used, even the isotopes that might be used to, power satellites, make those the radioisotope, batteries. Also, as we mentioned, the cancer, a lot of things for cancer research, and just general research using radioactive materials to learn about how interactions of things. A lot of the information we understand are from radioactive materials. The research we've done to see how the stuff in the cell works, all that was with radioactive materials. So they either made the radioactive material, either at a reactor or accelerator, or they, took it from nature, they culled it down and, separated that radioactive material and used it, so.
Okay, we're at the top of the hour. Candace,
Oh,
always
okay.
wonderful to work with you again. That concludes tonight's webinar. Thank you all for attending.
All right, bye.